It's my pleasure to have you here, Jeremy. So Jeremy is a famous Haskell programmer with a long career and many contributions to the Haskell community. So now we're going to hear about something interesting about streams.
Right, yes, thank you very much, Rosie. Pleasure to be here. Thank you everyone for coming. I'm going to talk about a draft paper. It's under review at the moment, and at the end there's a link to my webpage where you can find a copy of the paper. I hope the passing reference in the title was clear. It's about well, it's kind of inspired by and in tribute to David Turner, who died last year, but also to Richard Bird, who died a couple of years ago. Richard was my field supervisor, so everything I learned from him. But David was also very influential, and there's a couple of particular influences from David that I'm going to talk about here. So this is about the sim of Eratosthenes, a cute program for generating the primes, and contributions that David and Richard had to this. So David started a DPhil at Oxford a long time ago, so 1969 under Christopher Straight. He spent his 3 years in Oxford and then had to go and leave and get a job without completing his DPhil. He was doing something with this language called PAL, P-A-L, which was a language that Strachey was working on at the time. Then he left, went to St Andrews, started teaching and got given the functional programming course to teach, which when he was given it was taught in Lisp. So he managed that for a year, but got dissatisfied with Lisp as a language for teaching programming. I mean, it really was Lisp at the time, not Scheme, of course. So the Lisp with its crazy dynamic scope. So he thought this was mad, and wrote his own language, which he called St Andrews static language, static scope rather than dynamic scope. So where the binding occurrence of free variables in a function definition is at the point of definition rather than the point of use. And Sazzle was, I mean, a small language, a homegrown language used for teaching. David was very keen on thinking about how to express programs and what are the right notations for doing this, and designed the language very much with program expression in mind. So what are the right tools for expressing our algorithmic thoughts? One of the things that Sazzle didn't introduce but popularized is what we now call list comprehensions. David in Sazzle called them ZF expressions, and Frankel expressions, so like set comprehensions but for lists. David got them from a language, got them from a language called NPL.
It doesn't have sound.
Oh, okay. So do you not have sound on the Zoom?
No, they said they don't.
Yeah, because some people don't heard us.
Baruch said it's fine. Yeah. Baruch says it's fine, Martin.
Okay.
Well,
We do. It's just a passing moment. Okay, I wonder what you missed. So David, I think, got these list comprehensions from NPL, which was an Edinburgh language, a predecessor to Hope. Actually, I've looked into this before for another paper. I think the idea of list comprehensions or set comprehensions in programming comes from a language called Settle, which was Jack Schwartz at NYU in the late 1960s. And I don't really know how they got from there to Edinburgh, if that was independent or not. But anyway, list comprehensions is one of my dramatis personae, and that's David's contribution. David also was a proponent of lazy functional programming as opposed to eager functional programming. So the first version of Sazzle that he implemented was eager, and in about 1976, he revised the implementation for the next academic year and switched to to lazy evaluation. And this particular, he writes about this in a sort of retrospective paper. His particular purpose for choosing lazy evaluation was validity of equations. He was thinking about writing programs by writing equations, and those equations should be valid and usable for reasoning. And the program that you express as an equation only works as an equation if it's read lazily, or at least called by name. Where you say f of x equals 3, and you expect everywhere f of x to be equal to 3, you want that to be true for all expressions x, not just all values x. So even f of undefined should be 3 if it's going to be f of x for all x. So that requires something like lazy evaluation. Sazal switched to lazy, and David kept using it, kept developing it. He moved from St Andrews to Kent, made a new version which was called KRC, the Kent Recursive Calculator, which was an even simpler language. And the idea there is basically you only have a REPL. It's like a calculator, so you type things in and it gives you values for them. It's a REPL which you can define new functions, but you're not expected to write long programs in KRC. You're only expected to write one-liner kind of things. KRC evolved into Miranda, and Miranda is almost what we have for Haskell when the Haskell committee was formed to unify a whole bunch of different lazy functional programming languages in the late 1980s. The committee asked David and said, well, Miranda's perfect. Why don't we just adopt Miranda and make it the community standard? And David said, no thanks, I don't want you all messing with my language. Not for that, we would all programming in Miranda. I forget the timeline, but around this time, so early 80s, David was thinking about compilation for lazy functional languages, and he did it compilation through combinators. So there's a paper in Software Practice and Experience explaining how this works, and some other papers where he talks about Miranda and KRC. And so he, at some point, eventually returned to, well, finish writing his dissertation and submitted it and got his DPhil. In fact, he didn't finish writing his dissertation. He chucked all that stuff about POW away. Strachey died in 1975, something like that. So formally it was Dana Scott who was David Turner's supervisor by the time he submitted. But lazy evaluation and list comprehensions are two things that David Turner didn't invent either of them, didn't introduce either of them for the first time, but did popularize them and did argue strongly for their benefit. And they're going to be the ingredients for this talk. Richard Bird, kind of similar, started a PhD in London in 1973. Started a PhD in London before that. It would have been about 1969, about the same time as Turner, I guess. Lectured in Canada for a year, got a lectureship at the University of Reading, was allowed at Reading to finish off his PhD in London. And that was about Turing machines and sort of general theory of computation stuff. But Richard was particularly interested already in the early 70s about when two programs are equivalent and how to prove that two programs are equivalent, and how to transform one program into another program to demonstrate equivalence, or to come up with the second one from the first. And this led him to functional programming, to program calculation, where you start off with a clearest possible, simplest possible definition of the program that might be hopelessly inefficient, and then use meaning-preserving transformations to turn this into a manifestly equivalent program, but one that is acceptably efficient. He was also particularly interested in algorithm design and taught algorithms at Oxford, and he and I, one of the last things he was working on was a textbook algorithm design in Haskell. Privileged to be co-author with him on that. But he was never a compiler person, never particularly a language design person, but mostly thinking about how to apply programming languages and programming notations to questions of algorithm design. Richard is the sort of instigator of the idea of functional pearls. So when the Journal of Functional Programming started in 1990, the 4 original editors invited Richard to be editor for a column of functional pearls, which were inspired by programming pearls from communications of the ACM, John Bentley. So these are small papers, not necessarily making an original research contribution, but telling an old, possibly old idea in a new and compelling way. So Richard gave a keynote about pearls at ICFP in 2006, and among other things, he characterized that the pearls should be polished, elegant, instructive, and entertaining. So they should be very well written, very accessible to read papers. They should not be clunky. They should tell you something. You should go away with having learned something. It's not just sort of standard science saying we did this boring thing and it worked. That's standard, paradigmatic, good science, but that's not a pearl. And they should be entertaining. He kind of treats them as short stories. So don't worry about all the usual paraphernalia of introduction and methods and related work and so on. So leap straight in, start telling the story. Into the punchline, perhaps. So, second character, and the third is Eratosthenes. Of course, I don't have a photo of Eratosthenes, but he was a polymath. He was at one point the chief librarian of the famous library in Alexandria. He did all sorts of things. He's most famous not for what we know him for, but for calculating the Earth's circumference, which he did by measuring shadows at particular times of day and so on. But he worked out when the Trojan War was 1,000 years earlier. He invented the armillary spear, which is this brass mechanism that simulates the heavens, the solar system, or whatever. Well connected, taught by Zeno, a friend of Archimedes, and so on. We know him for what we call the sieve of Eratosthenes, the prime number sieve. I'll tell you about that. I quite like Eratosthenes because he was not universally admired by his compatriots. He was called Pentathlon, which I don't speak Greek, but means
5 prizes.
5 prizes, is it? Okay. So Wikipedia glosses it as an all-rounder. He was also called Beta because he was never the best at anything. He was second best at all sorts of things, kind of Jack of all trades. And somebody also said, I think some biographers have called him a mathematician and geographers and a geographer among mathematicians. So it didn't feel at home anywhere, and I have some sympathy for that. So putting myself on a level with Eratosthenes, I was never chief librarian of Alexandria. I sometimes feel between the two stools like that.
He would have been the best mathematician in the world, apart from the fact that he was a contemporary of Archimedes.
Well, yes. So, second best mathematician in the world, which is not bad. So, Eratosthenes sieve. This animation is from Wikipedia, so thanks Wikipedia. The idea is to generate all the primes. The Wikipedia version, and the version that most people know, is all the primes up to a given bound. So let's say we want all the primes up to 120. And the rule is, the first one is a prime, that's 2. And then you cross out all the multiples of 2 in what's remaining. They're not primes because they're all divisible by 2. And then the first one left, 3, is a prime. And then you cross out all the multiples of 3. You can start with 3 squared. Why is that? So this is only, I didn't cross out 6 here, we call 6 green.
Because you've already got all the ones beneath it.
Yes, so anything that's smaller than 3 squared and composite has a prime factor that you've already dealt with. So you can start with the square of this prime. So you start crossing out from 3 squared, then the next one, 5, is a prime, and then you start crossing out from 5 squared, and then 7 is a prime, and you can start crossing out from 7 squared, 49, and then 11 is a prime, and you can start crossing out from 11 squared, and there's no crossing out to do. So at that point, you know everything else is a prime, and everything you've not crossed out so far is a prime. That's the set of Eratosthenes. So David Turner used this program as an illustration of lazy lists and miscomprehensions. So there's a SASL manual. In fact, there are several SASL manuals, all with the same technical report number. So rather unhelpfully, David revised it. This one says revised 1st of December 1976. But it's CS 75/1 is the technical report. So somewhere between 1975 and 1976, David said, well, SASL should not be an eager language, it should be a lazy language. Let me update the manual. He sent it again around to all his friends. So Oxford was apparently friends at the time. So we, in our library, in the dusty boxes on top of all the shelves, unloved by anybody but me, apparently. We do have the 1975 and the 1976 versions of this tech report. I'm very grateful for our librarian for keeping them. Actually, I'm grateful for me for arguing that a previous head of department, not the previous head of department, shouldn't throw them all away. We haven't done with the library yet. These things are not available online, and they're important. So, in the 1976 version of the SASL manual, David has this program. So there's some exercises at the end, and one of the exercises is write a program to generate all the primes, use the method of Eratosthenes or something like that. And the answer, he gives the answer as well. This is the answer, this is the program. So in Haskell, we write it today. Primes is what you get by sieving the plurals, the numbers from 2 upwards. And to sieve an infinite list, P cons X's. The first thing, P is a prime. You remove all the multiples of X and sieve the remainder. So unlike the animation from Wikipedia, this one works on infinite lists. You don't have to lay out a table of the numbers up to a given bound first and do all the crossing out eagerly.
So that's list comprehension, is it?
That's a list comprehension. Right. Sorry, yes. So this is, in case you're not a Haskeller, the list of values X, where X is drawn from X's, and X is not divisible by P.
The ordering is implicit.
It's a list, so it gets them in the order that they're drawn from X's. So the order of the elements in here is the same as the order in X's. So it's not a list comprehension, it's not a set comprehension, it's a list comprehension. There is an order, and these things are generated from other lists, and the order comes from the other lists. Please do ask questions. But in contrast to the animation and the way it's sort of given in most textbooks, you don't have to say, well, I'm only going to go up to 120, let me make a table of 120. When I want to cross out the multiples of 7, well, I just go ahead and cross out the multiples of 7. I've got to stop somewhere, so I'm going to stop at 120. With lazy function programming, you don't have to stop somewhere. You can say, well, I'm going to cross out, eventually I'm going to cross out all the multiples of 7 from 49 upwards. I'll get to them at some point. And that's what the lazy program, the lazy list program does. So, actually, in 1976, SASL didn't have list comprehensions, so David had to write it with a filter, which takes a predicate and the list and removes all the things that actually it takes. This one's taking just the prime. If A is divisible by P, it's discarded, and otherwise it's kept.
So just because the language is not guaranteeing that this is infinite. I mean, we know that it's infinite, but this kind of syntax could produce programs which eventually just diverge.
Absolutely. This is going to be my point. hold that thought. So, David acknowledged, I think not in the Sazal manual, in fact couldn't have been in the Sazal manual. This is a quote from an email he sent me. Where did that program come from? When did you learn about the Civ of Eratosthenes? And he said, well, there's this paper by Carden and Queen, coroutines and networks of parallel processes, they would call them CARN networks now. David wondered whether he'd seen that paper. I didn't chase this up. This was an email at 2020, and I didn't chase this up then. The idea was still bubbling at the back of my mind. But last year, I went and checked out Carden and Queen's paper, and they credit this idea to Doug McElroy. Doug McElroy had another tech report, which from Bell Labs called Coroutines, which McElroy himself has put online, so you can find that now quite easily. McElroy also wrote about this in another retrospective, saying, I gave a talk in Cambridge, and I cooked up some interesting coroutine-based programs, and one, the prime number civ, became a classic, spread by word of mouth. And this is the diagram from, well, McElroy's later version of his coroutines tech report. But this is the prime number civ. Donk generates the numbers from 2 upwards. That's the source, and then each of these boxes is a filter. This keeps the 2 and then chucks out all multiples of 2, and then this one keeps the 3 and chucks out all multiples of 3, and this one keeps the 5 and chucks out all multiples of 5. And anything that gets through all these filters ends up in the hopper at the end. So that was McElroy's metaphor for kind of conveyor belts of stuff. I'm guessing, though I never got the chance to ask David this, I'm guessing that David learnt about the talk in Cambridge in 1968. So probably, perhaps Strachey was at that talk in Cambridge and showed it to David, his DPhil student. But we can't ask that now. So, unfortunately, the program that David called the method of Eratosthenes, the Civ of Eratosthenes, and Carden and Queen also called the Civ of Eratosthenes. McElroy very carefully perhaps didn't. He just calls it prime number civ. It's not the Civ of Eratosthenes. It's an imposter. So there's this lovely paper in Journal of Functional Programming by Melissa O'Neill in 2009 about the genuine Civ of Eratosthenes. And Melissa O'Neill's point is that what's wrong about David Turner's program is that for each prime you go through every remaining candidate X, testing for divisibility by P. You don't need to do that, and the Wikipedia animation shows something different. You don't, when considering the multiples of 7 from 49, you don't consider 49 and then 50 and then 51 and then 52 and then 53 and so on. You consider 49, you cross that out, and you jump straight to 56 and cross that out and jump straight to, so you only cross out the ones you're crossing out without considering all the ones in between. So you proceed in longer and longer strides over the remaining numbers. I think that's what Melissa O'Neill counts as the genuine Civ of Eratosthenes, and something that goes through all the candidates one by one for each divisor is not. And Melissa O'Neill calls those just trial division, generating the primes by trial division. So Melissa's moral in her paper is that you can do it using priority queues instead. When you find the 2's a prime, you make up something that is going to go through with strides of 2. Sometimes those are called wheels, prime number wheels. You think of it as a wheel with circumference 2, and it rolls over the numbers, and every time it completes a rotation, it crosses a number out. Then you have a wheel with diameter, circumference 2, wheel with circumference 3, wheel with circumference 5, and these wheels run in parallel and cross things out. If you try a bit harder, you can turn a wheel with circumference 2 and a wheel with circumference 3 and a wheel with circumference 5 into a wheel with circumference 30 with marks at various places. And those wheels, if you're going to run them lazily, you want to maintain a priority queue of when is the next wheel going to have some interesting events happening on it. So these wheels are sorted in a priority queue, maintained in a priority queue, with priority, the next number they're going to knock off. And so when you find a number, you cross that one off, and then you take this wheel and stick it back in the priority queue at some later period. And so Melissa O'Neill's point is that we don't need to do everything in terms of lists for functional programmers, and lists are very convenient. And Lisp, which is arguably the first functional programming, is even named after doing things with lists. But there are other data types too. So she in particular says, well, we should be thinking about priority queues. That's the right way of implementing the SIP of Eratosthenes. And she's got some programs with priority queues in this paper. That's the P-squared question again. Now, again, I don't know this, and I can't ask Richard anymore, and I've written to Melissa O'Neill and she hasn't answered. So
Why a priority queue? I mean, if you look at the popular presentation of the sieve, it looks like an array, not a priority queue. You use the index to compute what you keep and what you delete.
right, but you can't do that easily because it's now an infinite array. So you have to sort of maintain a to-do list of the numbers you're going to cross out. I'm going to cross out all the multiples of 2 from 4, and all the multiples of 3 from 9, and all the multiples of 5 from 25. And then you spit out numbers, keeping an eye on what the next thing you're going to cross out is. So you've got the to-do list now is a collection of things you're preparing to cross out. And how are you going to organize that so you can quickly find the next thing to cross out? Well, you want them organized by the next multiple of 2 to cross out, the next multiple of 3 to cross out, the next multiple of 5 to cross out, and labeled by their index by their priority, which is the next one.
I mean, it sounds also like it's not like a bit of an interpretation of the sieve.
Well, I don't think we have whatever Eratosthenes might have written. We've only got several people's other interpretations of it. And well, I don't know how McElroy ended up with it as a network. He would have learned it from somewhere. It is, I think it's in Knuth's Art of Computer Programming, semi-numerical algorithms, but that's volume 2 is 1972, so that's post McElroy's talk in Cambridge. So that's not where McElroy learned about it. I have no idea where he learned about it. I don't have earlier references to the kind of thing that people like McElroy would know, unless it's just that McElroy is very, I think still alive, is very well read and knew the ancient Greek stuff. Or maybe he was taught at the school, who knows? I mean, but yes, absolutely. These are different people's interpretations of things. So I think Richard would have been the handling editor at Journal of Functional Programming for Melissa O'Neill's paper. Melissa O'Neill's paper is not listed as a functional Perl, so it didn't directly fall into Richard's domain. JFP doesn't record it as a Perl. Richard does write about it and calls it a Perl, but I think that's a misnaming. But nevertheless, the JFP editors will have received Melissa's paper and given it to the most appropriate editor, which might well have been Richard anyway. So I'm presuming that Richard was the handling editor. And he would have read the paper and sent it out to referees and said, yes, very nice. But have you considered this? Here's this fancy program that you've written with priority queues. You can do it just with lists. So Melissa O'Neill includes Richard's program, doesn't say it came from the editor, but said it came from Richard Bird in her paper at the end of the paper. She says it's a little bit slower. I don't follow the reasoning for that, and I don't see why it should be, but that's a separate question.
Sorry, the n here is it the bound you're starting with, or the length of the bound?
It's how many steps it takes to compute the first n primes. Or maybe the primes up to n, I'm not sure. But
Okay, so it's exponential on the length of the invert.
it's log n, so it's a very small.
It's log in the length, yeah.
It's log in the length, not exponential. And I have thoughts about that, but Melissa hasn't replied to my email. So Richard wrote Thinking Function with Haskell in 2016, I think. So this is kind of the third edition of his book on functional programming. And he includes his program from Melissa O'Neill's paper in Thinking Functionally with Haskell. In the chapter about infinite lists and proving things about infinite lists, and then sets the proof of correctness of this program as an exercise. And in the book, there's a whole bunch of exercises, and every exercise has a solution, so there's a solution to this exercise as well. The solution is just a hint, and unfortunately the hint is wrong. So I ended up with handling the errata for Richard's book, and some very careful reader said, this doesn't seem to make sense, this obviously doesn't work, and I'll show you what the reader said, Francesco Lieberich. And for some years, I've been puzzling about what I should put in the errata for the book for that exercise. So here's Richard's program. The primes and the composites are a list of integers, and here I mean streams of integers, so infinite lists. And they're all going to be, and actually I mean streams of naturals, although I don't have a natural type in plain Haskell, and they're all strictly increasing as well, no duplicates and ordered. The primes are what you get by taking the plurals 2 upwards and removing all the composites, and this is subtraction of difference between 2 infinite lists. And the composites are what you get by, for each prime p, generating the multiples of p from p upwards, so from p squared upwards, right? So p squared plus p squared plus 2p. Each of these is another one of these infinite, strictly increasing lists. And this is an infinite list of them, one for each prime. And you merge those all into one long list. They're all the same length, of course, but you merge an infinite list of infinite lists into an infinite list. And then, so this is the obvious definition of difference between 2 lists. If the thing you've subtracting from has a head which is less than the thing you're subtracting, then that is in the result, and you continue with the remainder. If there's a match, you remove that and continue with both remainders. And if the first thing in y's is smaller than x, then that's obviously not present, so you just consider all the remainder of y. So you hang on to x because you might still delete it. Here's merge, and again the obvious definition. And the same recursion pattern, and I'll let you work out the program. There's no duplicates, so if you're merging and you find a match, you only keep one copy as a result. And then merge all is actually it's a fold over stream. So if you can merge 2 streams, then you can merge an infinite stream of streams by merging the first list with what you get by merging all the things in the table list. Table of the list. So nice program, doesn't work. So the wrong reason it doesn't work is it's not quite productive up here. So the change was it's not. So this says to generate the first prime, you need the first composite because you need to do a subtraction, and to generate the first composite, you need the first prime. So that makes it work. However, if you prime the pump, so to speak, by saying, well, let's start with 2, and then it's 3 ... less the composites. That turns out to be enough to get things flowing. Still doesn't quite work. And you have to be a bit clever here with this merge. So actually what we want to merge is an infinite stream of infinite ascending streams. And you can't always do that. So these ones do merge to make an infinite stream. But what if I've got 4, 6, 8, ... 3, 5, 7, ... 2, 4, 6, ... where the heads of the streams get smaller and smaller. There's an infinite list of them. There is no smallest one. So there's no merge for those. So merge all obviously can't be productive as written. It's not going to work always. However, under the assumption that the heads are themselves strictly increasing, you can say what merge all is going to do is blindly choose the head of the left-hand stream as the first output, and then go off and do the ordinary merge from there on.
If the streams are all streams of natural numbers, that should be fine, the first solution.
If they're natural numbers, that will be fine. If they're integers or rationals,
Yeah,
or whatever, then yes. But as a Haskell program, it's polymorphic, so it's not taking paying any attention to what their actual elements are. It's just using.
Right, it's not well defined by virtue of the code written.
Yes. But these two changes, priming the pump and taking account of the fact that these streams are ordered by their heads, makes this a productive program. So it's slightly delicate because of those two things you need to fix. But morally, the first program I showed you is the right thing to do. And it's a cyclic program. So primes is defined in terms of composites, composites in terms of primes. Does it work? And it does. You can sit there and watch it spit out primes. But how do we know it does? So in the book, Richards talks about using what he calls the approx lemma for proving two infinite lists equal. So here, approx takes an int, well, again, it's going to be a natural number, and a list, which might be a finite list or an infinite list, or indeed a partial list, one that ends with undefined partway along. And given some bound, it gives you that many constructors, up to that many constructors in the list. And then it stops. It gives you undefined from then on. There's no case for approx 0, so approx 0 x is undefined. So this will give you, approx n x's will give you the first n conses or nil of your list, but then run out when the gas runs out. And then the approximation lemma says that two lists are equal if and only if all their finite approximations are equal. So, and proving things about limits in terms of all finite approximations. And this is quite a useful tool for proving things about lists. So then, in the body of the thinking function with Haskell, Richard says, this is primes, this is my circular program. Let me consider the nth approximation. I want to show that it's the first n primes and then undefined. Given this, it's sufficient to show something about the corresponding thing with the composites. So the composites are the first few composites. And then the proof is computed by using this thing here, which is a non-trivial result in number theory. That's a consequence of what's called Bertrand's postulate about how spread out the primes can be. Details are in the exercises. So in fact, there's a typo in the book that it says n means Cn. So the pros-n is the first n primes, and cros-n is the first m composites. What's n? Well, never mind what n is. It's the composites up to the square of the nth prime. So details are in the exercises. Exercise I in that chapter says recall these definitions here. Given that these primes show the crozes those composites, again, there's the same typo. Hence show that primes does indeed produce the infinite list of primes. And then the answer to exercise I is the proof is by induction. Again, it's the same typo there. So we first have to show that the next approximation to the composites is the result of merging the previous approximation to the composites with some multiples. And that gives the partial-decimal composite, or the next approximation to the composites. And finally, we need this result, which is a gadget from number theory. And my correspondent, Francesco Liebrig, wrote back to me, sent me an email saying what this can't be right, because what it's saying, for example, when n is 2, plus 2 is the composites up to the square of the second prime. For better or worse, Richard numbered the primes from 1, so the first prime is 2 and the second prime is 3, so this is the composites up to the square of 3. This is the composites up to the square of the third prime, so it's the composites up to 25. And he's saying what we have to show is you get Cruz 3, this thing, by merging Cruz 2 with the multiples of 5 from 5 squared upwards, so 25, 30, and so on. You don't get 4, 6, 8, 9, 10, 12, 14, 15, etc. by merging 4, 6, 8, 9 undefined with some numbers from 25 upwards. So that's not the right hint. And what should the proof be? And as I say, I've been puzzling about this for several years, and I've regaled various colleagues saying, well, what should I do about this? I do have a proof now, and it's in this draft paper, which has the same title as the talk. It's on my webpage if you want to check it out. I'm not going to show you the proof here because it's still 7 pages long and quite laborious, and I'm not entirely happy with it. But this was submission with a deadline, so I haven't got reviews back yet, but I still plan to think about it. But I will show you there's 3 key points in the proof. How long should I go for?
Well, you just finished 10 to so that people can ask questions, but the people have asked questions during the talk, so I guess we can go.
Is the room booked from the next
I don't know, we can check.
I'll try and be quick then. So the second proof technique that I found useful, found helpful, is so analogous to the Cross-Lemma, but different, is proving that to prove 2 lists equal, it suffices to prove them equal on all questions of membership. So these are really proofs about sets. So 2 sets are equal if they have the same members. Now, this is a little bit subtle. I've defined membership here on these infinite streams, and I'm assuming they're infinite, again, strictly increasing. So you can answer false for membership here, which you couldn't do if it was just simply an infinite list.
Okay.
So on a strictly increasing list with fully defined elements, this function is total. For a partial list, it's still defined up to the last present element, so the last properly defined element. So if it goes 4, cons 6, cons 8, cons 9, cons undefined, you can ask about anything up to 9, whether it's in that list, and you'll get true or false. If you ask about anything greater than 9, you'll get undefined. You'll fall off the end of the list. So for strictly increasing lists, infinite, or they can be partial, works true for ones that run out part way. The element type has to be flat, so the elements have to be all properly defined. I'm not having lists with undefined elements. The cons cells could be undefined, but the elements can't. And then this result holds. And it's not true if they're not increasing. It's not true even if they're weakly increasing, because they can agree on membership and be different lists when there's duplicates. It's not true about finite lists, because the empty list and the some reason. It's not true with finite lists, and it's not true if list elements can be undefined, because you can't distinguish between something falling off the end or something in an undefined at the end of the list. But all these conditions work in my context, so this number works for me. I need, as well as approx, so I want to talk about the first n primes, the first few primes, and that involves talking about the first few composites. So the first n primes involves talking about the first, well, how many composites? It's the composites up to the square of the nth prime. Now, a little bit of ingenuity, you can work out how many there are, because it's the square of the nth prime minus the number of primes, so the composites, the rest, minus 1 or 2, because you start counting from 2. But that number is not a very helpful thing to be working with. So it's more convenient to say, well, the first n primes correspond to the composites up to the square of the nth prime. So I want approximations up to the value rather than approximations for a certain number of elements. And then, because I'm doing subtraction on these things, I want the one element beyond the end of the thing I'm subtracting in order to know that to deal with the end case. I need a kind of sentinel at the end. I need an approx while and an approx until with kind of behavior that you can reconstruct. So that's the second gadget, and the third gadget is Bertrand's postulate. So the key step is to say, well, here's the primes done in the most obvious way possible. And the primes and the composites, the specifications of them are what you get by partitioning the plurals on whether or not each of them is prime. And I'm just going to give you the most clearest, simplest definition of primality. So then the key step in the proof is that the nth approximation of the primes is indeed agrees with the specification, and the composites up to the square of the nth prime agrees with the specification there as well. We need to prove both of these things by induction at the same time, because they depend on each other. And it exploits this key result from number theory, which is a non-trivial result in number theory.
Is that a typo? Should it be Pn plus 1?
It should, thank you, yes, it should be Pn plus 1. So in fact, Bertrand's postulate tells you that Pn plus 1 is less than twice Pn. But what we need is less than the square of Pn, but twice Pn is itself less than the square of Pn, because all the primes are at least 2. So this is the convenient form, and that sort of matches nicely with this condition. So yes, that's Pn plus 1. I haven't looked into a proof of Bertrand's postulate, but it's something that was postulated, obviously, and then only sometime later proved. So it's not a trivial result, which calls it a non-trivial result.
So it was proved by somebody else?
Chebyshev.
I think actually this weaker version was proved before the full version.
Okay.
This is easier.
This is easier, is it? Right. Yeah. I still don't fancy doing any of them. So, back to David Turner. So one of the last things, not the very last thing he was working on, but one of the last things he was working on was a project we called Total Functional Programming. And there's a couple of papers about it. This one was from 2004. And he was saying, well, we ought to, if we're going to take this equational reasoning with programs seriously, we ought to treat the programs seriously. And when they define things, they better define things. And he wanted to exclude the possibility of non-termination. So this was Paul's question about possibly non-terminating things. So one necessary step is to make a clear distinction between finite data and possibly infinite code data, which is something many of us know and love. David was hoping for something much more modest than Agner or Koch or constructed type theory or full dependent types or whatever. He was he says he's aware of these things, and he says, I know of these things, and I know in principle they solve the problem, but that's not what I'm looking for. I want something that looks much more like an ordinary programming language. I want something like hinting on the typing just with data and codata. And I want to be able to write programs without having to encode proofs of things in the type system. But still, I want to be able to be convinced that these things are productive. And he did contemplate the consequences of this wish. So he says most of the algorithms we ordinarily write are already, didn't use this word, but structurally recursive. So they're already folds over the data or they're unfolds, so they're necessarily productive. And even the things that we don't write this way, we can re-express them this way. And one of the examples he gives is quicksort, which you can think of as a tree sorting algorithm. You take a sequence and you partition it into a tree using an element as a pivot and little things and big things. And that's kind of obviously structurally co-inductive to grow the tree because each of the two sublists is shorter. And then obviously concatenating the tree back to a list is obviously inductive. So that's obviously structurally fine. My conjecture, with more practice, we'll find this is always true. But he also says in the same paper, sometimes it's quite hard. For example, writing the well-known Sieve of Eratosthenes, by which he means trial division, not the clever cyclic program. If we were to do this, then somehow we have to encode some bound on the distance from one prime to the next. I was reading some other papers that people have pointed me to last time I gave this talk on the train on the way up here. I do have ideas about how to do this for actually the trial division program. I have no idea how to do this for the clever cyclic genuine Sieve of Eratosthenes program. So some work in dependent types, Yves Berthaud, Pierre Casteran, Christine Bourlin-Morin have written programs that do trial division in Coq. And so either you cheat by saying, well, I'm not going to filter and produce only the primes, I'm going to produce maybe primes, so it'll be primes or nothing for the composites. You have to work a bit harder to prove that you haven't missed any primes that way, because the types only say you could return all nothings. So as long as you can encode sort of the bound to the next prime, as David says, Berthaud has ideas about modal logic, temporal logic. So you want, there's an always eventually property. For every prime, there's always eventually another prime. And you can encode that with some kind of inductive recursive thing. But I don't think that helps with the cyclic program.
How precise that bound is doesn't matter for the efficiency of the program, right? It's just something that strictly is in the proof, and then it's ignored at runtime.
I think that's right. Yes.
So you could maybe can you make a proof easier just coming with some kind of like an absolutely trivial bound, like I mean a very imprecise huge bound which is still finite.
Euclid's proof of the infinity of primes by multiplying all the primes you've got and adding
exactly.
That would suffice. Yeah. You can encode that for the trial division program.
For the trial division.
But this mutual co-recursion between the primes and the composites in the genuine program, which is genuine program. I don't see how to do that. I'm no expert dependently type programmer, so I look forward to being shown how to do it. I'm here all day, by the way. So I'm going to stop there. David Turner had laziness and list comprehensions, and used what he called the Sieve of Eratosthenes, but is really just trial division to illustrate and promote those ideas. And there's this nice paper by Melissa O'Neill showing how the genuine Sieve and the difference, and Richard's clever list-only program that implements that. I have a long and unwieldy proof, which I'd love to be shorter and simpler, and I'd even more like to see how this could fit into David Turner's vision for total function programming.
Thank you very much.